Shukai, does it work? Shukai, does it work? Okay. Okay. Let's start. So first of all, this is our last lecture in this semester. So thanks for all of you coming from this, snowing and raining day. So we're gonna first spend like about 20 to 30 minutes to give a quick review, and we'll talk about how are we gonna schedule the final exam and what is the coverage, what are the problem types, what's the suggestion to do some effective review. We don't want you to like spend 10 days and looking at every details. That's not necessary. So as we discussed previously, so the final exam will be some kind of like a concept checking, like to ensure that you know those ideas we have discussed so far, and you can differentiate different strategies and avoid like common mistakes in understanding machine learning models and algorithm and concepts, etc. And then we'll talk about in practice how should you make your machine learning model work, and how to integrate your machine learning component with many other components in a large joint system. Actually, this is how machine learning is used in practice. This is quite different from like machine learning homework assignments, right? You implement a specific model in you have all the data set ready, and those data set has already been pre-processed, and what you need to do is just to report the prediction accuracy and so on. Right? But in practice, the task is really highly complicated. So your machine learning model, which might be critical, but only fulfill one subtask. There are many other tasks that need to be fulfilled by other components, and your machine learning component and all the other components like data pre-processing, infrastructure, those kind of stuffs are kind of coordinating with each other. They have a kind of a complex relationship. And how, in that case, how do you analyze the bottleneck of your machine learning model? How do you find out the reason why your system performance is low, right? And find a way to improve each component is very critical. So that's we're gonna discuss after we do this quick review. Okay. Yeah, but again, if you haven't started homework 5, please do it as soon as possible, because tomorrow will be data. Okay. So first, let us talk about the final exam. So as we highlighted in the course website, and also made an announcement in the Canvas, our final exam will be on Wednesday, next Wednesday, December 15th, of course, 2021. And it is from 8 a.m. to 10 a.m. So it's quite early. I don't know why this university, schedule this time, but we have to stick to their schedule. And our exam is online, so you don't need to rush to the classroom. So just open your desktop or laptop and log into Canvas. And when you can go to the quizzes section, and there's one exam or quiz waiting for you. So it will strictly starts from 8 a.m. and ends at 10 a.m. So don't miss that time window. And if you miss that, you won't be able to open the quiz. And we'll keep reminding you, following a few days, right, to ensure everybody won't miss this important schedule. So final exam policy, as we have discussed before, right, and also at the beginning of this semester, our exam is open book, open website, meaning that you can access the course website and download the PDFs, or you can bring your books or whatever, whichever you want, right? But we do not allow search or posting questions online. So don't post the question on like stackoverflow.com and waiting for their answers. And don't text messages or send Facebook messages or whatever to your friends and to others, to your fellow students in this class to discuss. That's not allowed. And this is regarding the policy about what type of the problems you will see in the final exam. Right? So this exam is online, right? So it's kind of like a infeasible to ask you to prove a very hard to give a very hard proof or to calculate a lot of things, right? Like asking you to calculate a Gini index for decision tree, right? So we won't ask you to do that during the final exam. Instead, most of the questions are just the single or multiple choices. So we may ask you, we may give you a list of statements about decision trees, and you check out which statement is correct. Right? There might be 2 of the 5 statements are correct, or just 1. Right? It's typical multi-choice, right? And again, those single multiple choice problems are mainly used to check if you truly understand those basic concepts about models, algorithms, etc. Right? And we might have some test description. Like there's no need to write out any math formulas or whatever. For example, I'll ask you to write down your understanding of the PAC learning, right? Probably approximate correct learning, right? What does probably mean? Right? What is called approximately? Right? We may ask you to write down your understanding of that, and try to be concise. Right? Don't write an essay for this question. If you have multiple points, just list the points. Point 1, point 2, point 3, each point like 1 or 2 sentences at most. And the last thing is that the problems can vary for different students because we actually have a library of problems, and they have kind of like a random shuffling and random sampling from those questions to form the exam for everyone. So but those problems are kind of in the same level. So they are fair, but doing this is just avoid everyone, to communicate with each other because your problems might be different from others' problems. Okay, any question regarding the exam policy and the schedule? Okay, great. So what's the range, right? And because we don't have a midterm exam, right? It's not like other exams, like they often have like extra midterm exam. We only have 1 exam, so our coverage will cover like whole semester what we have discussed so far. And but we don't want you to like memorize everything. We highly suggest you to first review the lecture slides. And if you are familiar with those content and the review of the lecture slides are really quick. Right? You don't need to do the mathematical check of those derivations. That's not necessary because we won't test on that. But you do need to know which step causes the next step, right? The whole reasoning process. For example, in the small vacuum machine, right? We talk about dual form, right? How do we derive the dual form? How do we simplify the dual form? And from the dual form, when we solve the dual form, how do we recover the weight vector, the bias parameter? Like we know that the recovery of the bias parameter needs to combine those the KKT conditions and something with some intermediate results when we simplify the dual form, right? So I believe that if I have down this homework for homework 3, no, 4, 3, probably 3, I forgot. Carefully, you're quite confident about that, right? But those is just to give you a quick review, like you can connect them together fast, so that if we have some kind of questions asking you that, you can quickly identify which slice, right, which particular location, which that can help you answer the question. That's it. So we'll suggest you to review the lecture slides, like spend 1 day or 2 at most. And also to deepen your understanding or to refresh your memory, right? You can go through the paper problems in the homework assignments, right? So again, you don't need to do those calculations. But from looking at paper problems and from looking at answers, we have released the homework answers, right? So by looking at homework answers, you kind of catch what we have discussed before, right? And you don't need to look at the programming problems. We won't ask you to write down a pseudocode, say to implement the stochastic gradient descent. This is not what we want, right? We believe that through some real implementation, you have know those skills. You have the skills to implement, right? There's no need. There's no sense to check that again. Okay. Any question regarding the range? Everyone is comfortable? Great. So throughout this semester, I mean, very generally speaking, right? We have we started to define machine learning, right? What is the definition of machine learning, right? And under this definition, we have seen a variety of learning models and algorithms. And by looking at those models and algorithms, we kind of abstract several different learning principles, right? And we give a introductory discussion about learning theory, right? So we're not going too deep in the learning theory, but we introduce the fundamental concepts, right? What is the idea? Like agnostic learning, right? From agnostic learning, we can derive some sample complexity bound. We can derive generalization error bound. We can use bound to stimulate our design of new learning algorithm, right? And also a very important portion for this semester is the implementation practice, right? I believe everyone has done a lot of such kind of practices. So the definition of machine learning, I mean, the key to the definition of machine learning is the generalization, right? In other words, we will learning as getting a capability of generalization, right? Meaning that, okay, you say this set of examples, right? You know how to deal with new examples. If you say this example, you only deal with these examples, that's not learning, right? That's memorizing, right? Let's just memorize those examples, right? The learning essentially is to gain a kind of ability to deal with new situations. Right? So I'm gonna read the definition from Tom Michel again, right? We read through it in our second lecture in this semester, right? So a computer program is set to learn from experience E with respect to some class of tasks T and performance measure P if its performance at those tasks in T measured by P improves with experience E, right? So E is really referred to as training data, right? So we got some model, and when we feed those training data E to our model, we expect that our model can improve the performance in similar tasks, right? But different tasks, although it's kind of the same family, but different tasks. And this improvement can be explicitly measured by something, right? Like test accuracy, like like a square error, all kinds of stuff. Right? So hopefully, when you have saying quite a few detailed models and algorithm, we will look back at this definition of machine learning. You got better understanding or deeper understanding about this definition. So here's the framework of or formulation to conduct machine learning. Right? We have given the concept and how do we conduct machine learning. Right? To conduct machine learning, especially supervised learning, right? We need to define or we need to specify what is the instance space, right? And what is the label space. So instance space are the space including all possible training examples, right? And training inputs or feature vectors and so on. Right? And the label space are the set of all possible labels. So the type of label space determines the type of problems. If your label space just includes two labels, right? Binary label 0 or 1 or -1, 1. So this is called a binary classification. If your label space has multiple discrete labels like 1, 2, 3, 4, this is called multi-class classification. If your label space is continuous, right? Any real numbers can be a particular label. Then what is the task? Regression, right? Exactly, regression. So that's why we see like label space actually defines the type of the problem. Right? And then suppose you have got clear about your label space and your instance space and your label space. We believe that there is a mapping, right? There's a ground truth mapping which map the instance to the label, right? So we call this ground truth mapping as the target function. And the goal of our machine learning is to estimate this target function from data. So, and then to conduct such kind of learning, right? You have several protocols, right? Like supervised learning. You're gonna collect a set of pairs of instance and the ground truth label, right? You might collect like n pairs of such training instances, and then you feed those labeled training instances to our learning algorithm. And through some kind of searching procedure, right, you kind of identify which function you believe is closest to the target function. Right? So this is your learn function, and we also call it hypothesis. Right? So this is a supervised learning protocol. Right? And if you want to conduct unsupervised learning, you just get rid of those labels, right? F of x1, f of x2 to f of xn. So suppose you even do not know the ground truth label given by target function, right? You just feed the input instances to our learning algorithm. Can you still learn a function g which maps x to y? Right? So if you conduct a learning procedure like that, it's called unsupervised learning. So due to the schedule, right, tight schedule, we didn't get a chance to talk about unsupervised learning, but to the idea, the framework is kind of similar to supervised learning. Again, you're gonna define some loss function. You want to minimize the loss so that you find this hypothesis G, right? And also we can, combine a set of labeled training data and a set of unlabeled training data, and then we feed them to our learning algorithm. This is called semi-supervised learning. Again, it's kind of a natural extension to supervised learning or combination of supervised learning and unsupervised learning. Okay, so those are the general definition of machine learning and the framework, right? And then throughout this semester, we're actually are right under this framework and talk about a variety of learning models and algorithms, right? So just list them, like decision trees is the very first learning model we have discussed, and boosting ensembles, right? So we talk about ADA boost, we talk about random forest. Then we switch to linear models, right? we first discussed linear regression, right? We introduced the so-called least mean square method for linear regression, right? And we talk about how to minimize this least mean square loss function, right? With gradient descent, with stochastic gradient descent, right? Then we'll talk about linear classifiers, right? We start with the very simple heuristic rule-based linear classifiers called perceptron, right? It's kind of online learning, lazy learning. Then we move to a much more powerful and classical algorithm called the support vector machine. We spent quite a few lectures on talking about that because it's really, really important. Like it's a kind of a perfect, elegant combination of machine learning theory and also the practice, right? And then we talk about the kernel tricks, right? And how do we extend existing linear classifiers to nonlinear classifiers without changing too much of the training procedure, right? So that is the kernel trick. And then we can use kernel trick to fulfill kernel perceptron and kernel SVM, right? They're kind of nonlinear version of perceptron, nonlinear version of support vector machines. And next, we talk about another way to build up nonlinear models, right? So we talk about, okay, if you want to build up nonlinear models, we might just start with the existing linear models and then apply the kernel trick. This is one way. But another way is that I just want to build up nonlinear models from scratch. So artificial neural network is the typical approach in this strategy, right? With this strategy, and it's very popular and very powerful. So introduce the K technique in the training of the artificial neural networks, which is called backpropagation, right? So the backpropagation essentially is just a computational trick. Right? We try to calculate the gradient of the loss with respect to each neural network weight, right, very efficiently, right, rather than using naive chain rule, right? And that will be very costly, right? And then we talk about Bayesian learning, right? This is in our recent few lectures. So the Bayesian learning is another type of learning paradigm, right? We need to formulate the searching procedure in a probabilistic space, right? We need to assign the prior beliefs over the hypothesis in the hypothesis space, and we need to define or we need to model, given each hypothesis, what is the likelihood you see different training set. And you combine the prior, so you search the hypothesis who has the largest posterior probability given the training data, right? So the learning or the searching procedure in a Bayesian formulation is modeled as a posterior estimation procedure, right? So it's a Bayesian framework, right? And then we talked about two popular Bayesian learning methods. One is called logistic regression. One is called naive Bayes. Naive Bayes is what we have discussed on Tuesday, right? And logistic regression is essentially trying to learn a mapping from the input to some probability, right? Rather than some determinist label like 1 or -1. It is trying to predict the probability that your label is 1 rather than the probability itself, right? So the benefit is that, okay, I can tell how much confident I feel the label should be predicted 1, right? So those confidence or those uncertain estimate is important in many applications we have discussed a lot, right? Like recommendation, like online advertising and so on, right? And naive Bayes is another way of formulate the prediction, right? So you formulate the model, right? So we not only model given the input features, how do we predict the output? We also model how to generate the training features. Right? So we're trying to model the joint probability of the training inputs and also the training outputs. So in our prediction, we also employ the MAP principle to make the prediction. So anyway, these are just a brief review of those models and ideas, right? We just point out the key ideas, but we highly encourage you to look at the slides discussing those models and ideas and examples. So how do we characterize machine learning models? Right? We actually have multiple dimensions. If you just look at the type of models, namely what type of hypothesis, what type of hypothesis space they use, right? We can roughly categorize ML models in linear models and nonlinear models, right? So we have seen a lot of linear models, like least mean square method for linear regression, right? Like perceptron for linear classifiers, for support vector machine for linear classifiers, and logistic regression, well, is also kind of linear classifier, but we just predict the probability. And also, we talked about another very important type of models called nonlinear models, because the real world is always complex, right? You cannot always count on linear assumption. So in terms of how do we construct nonlinear models, we can roughly characterize them into two types. One is based on kernel, right? It's kernel methods. So kernel methods always start with some linear models. Then if you can smartly inject the kernel trick, like namely do some nonlinear feature mapping, and then your prediction and training is not really dependent on the explicit computational mapping. Instead, is the inner product. And then you can apply the kernel trick to avoid do this explicit feature mapping and dot product, right? So the kernel trick essentially is to calculate this feature mapping and then dot product in the original feature space. In that way, you can save a lot of computation. So, and then a second type of nonlinear models is just to build up those models from scratch, like neural nets, right? And also decision trees and ADA boost and random forest. So here, please don't be confused, right? Decision trees are not linear models. They can be highly nonlinear. So I don't know if you can recall, like when we talk about decision trees, we give some figure showing how the boundary, right? You can see that even for those binary features, like if you do some thresholding on continuous features, you got a set of binary features to create a tree. If you look at the boundary, it can be highly nonlinear. Not to mention their advanced version like ADA boost and random forest. They're often highly nonlinear as well. And so don't look down upon decision trees. They are very classical, very intuitive, but they're also very powerful. Okay, this is one dimension where we can view those machine learning models we have discussed so far, right? Another dimension we can see is the framework to conduct the learning procedure. So we can view them as probabilistic learning models or non-probabilistic models. Right? So probabilistic learning models like include logistic regression, naive Bayes, and a lot of models I'm doing in my research. Unfortunately, I cannot discuss in this class, right? But if you want to take my probabilistic learning class in next semester, you'll see a lot. For non-probabilistic models, basically says I'm not gonna use any probabilistic principle to define our model or to train our model. So those are actually the most models we discussed in the class, like neural networks, like decision trees, support vector machines, perceptron, and so on. But there's an interesting point here. We can quite easily convert non-probabilistic models into probabilistic models. So these guys all have the probabilistic versions or probabilistic counterparts. And so there's a very interesting, actually there's a very interesting research flavor that once some people propose some kind of non-probabilistic model, how do we turn them into probabilistic versions so that we can enhance that model by getting the uncertainty estimate of those parameters and prediction and so on. Okay. And in addition to those views, right, we need also to understand the basic concepts and conclusions in computational learning theory. Again, I want to emphasize that this is not a theoretical class, and our class concentrate on implementation and practical experience on that. By the same time, as a fundamental introduction level, right? We do need to know some important concepts in computational learning theory because those concepts are very important in the development of new machine learning models. So we introduced what is Pac framework, right? Probably approximate correct framework, right? We discuss why should we define Pac framework, right? Why can't we expect a machine learning model guarantee you some good performance, right? Why? Because the training data is uncertain, right? So if a high quality training data, well, you can expect your learning model can perform well, but what if your training data is bad, right? So that's why we cannot say, okay, my model can 100% sure give me 0.9 test accuracy, right? You always have to put some probability statement. That's why we call it Pac framework, right? So what is Pac learnability? What's the sample complexity bound? What is the generalization error bound? Right? You don't need to memorize those formula, but at least when we ask what is sample complexity bound, you should know what's the meaning, right? And what's the definition of visit dimension? And why do people propose visit dimension? Right? It's to address the issue that your hypothesis space is infinite, right? You want to differentiate the expressivity of different infinite hypotheses. Right? And how is the large margin principle derived by the generalization error bound and visit dimension, right? So there's some important concepts that are connecting together, right? Like data dependent visit dimension, and how does visit dimension is reflected in the margin. And also we need to know the principles to learn the models, right? Machine learning models like empirical risk minimization, it's called ERM. So empirical risk minimization essentially is to minimize the loss on the training data. That's it. We do not care anything. Our goal is just to fit the training data as well as good as possible. So know that there can be some issues because overfitting, right? So another more popular or commonly used principle is called regularized empirical risk minimization. So as the name suggests, right? So we just put a regularizer upon the training loss. So that means in the training phase, we're not only trying to fit the training data well, but also we kind of penalize over complicated models, right? So typical example is SVM, and also map estimation for logistic regression is another example. And when we talk about Bayesian learning, right, we talk about maximum A posterior estimation and maximum likelihood estimation. The difference is mainly in that in a map estimation, we're trying to incorporate some prior knowledge. Right? If you don't care about that, you just want to maximize the data likelihood. This is called MLE. So you can see that MLE essentially corresponds to the empirical risk minimization, right? Because both are just focusing on fitting the training data. And also from the learning algorithm perspective, we discussed gradient descent, right? This is kind of very simple, but the most popular approaches. As long as you can calculate the gradient of your objective function, you can just apply gradient descent. Right? And then we talk about stochastic gradient descent. Why? Because the gradient descent might be very expensive. You have a large training set. Suppose you have 1 million training examples. If you want to compute the gradient of the loss, you have to go through all the 1 million training examples, right? That is really expensive. So we want to conduct stochastic gradient descent to accelerate the updating of the model. Right? So doing stochastic gradient descent, whenever I meet one example, I just calculate stochastic gradient. I just update the model. So you can imagine if you go through this 1 million training examples once, you have updated your model for 1 million times. Right? It's very, very efficient. But if you conduct gradient descent, you go through the whole 1 million training examples once, you only calculate one exact gradient and perform the update for once. That's very inefficient, although this update is of high quality. So that's why in practice, especially with large data, we always favor stochastic gradient descent. Right? So you should be clear about their advantages and disadvantages. Right? And to conduct in the practice, right, there is an important problem is about hyperparameter selection. We have discussed that before, right? Like in SVM, we know there's the hinge loss term, there's the regularization term, there's a trade-off parameter C, right? To determine which part is way more important, right? And we have shown that you cannot directly optimize that. You have to manually select that. And very important idea is to use cross-validation. Or you can use a holdout data set and just train on the remaining set and say which hyperparameter gives you the best performance on holdout data set. So please be sure you understand those. Those are simple, but it's very, very useful in machine learning practice. Okay, so again, I want to emphasize the review suggestions, right? Go through all lecture slides, understand the details, and especially the definitions, right? The subtle difference between different models, and go through the homework problems you have worked. You don't need to go through the programming problems. And also you don't need to recalculate all the homework problems, just to be sure that what's the key idea to address these problems. That will help deepen your or reinforce your understanding of those models. Okay, so any questions so far for the final exam? Mm-hmm.
So it's like a 2-hour exam. You expect to stay 2 hours.
Well, I don't think, I think 2 hours is a little bit long for that. Many students, they can finish like in 1 hour, 1 hour, or 1 hour and a half, I guess. I would say it's easy. If you kind of feel comfortable with our lecture slides and spend some time review, it's not like everyone has to be in a hurry to finish all the problems. There are not too many problems. Another question? Perhaps I think 40 or 50 of I forgot. Yeah. It's not many. Other question? Okay, great. Hopefully this will be helpful. And now we're gonna use our remaining time to discuss some advice, practical advice when you deploy or build your machine learning applications. So we're going to talk about how do you deploy machine learning in wild or in real world, rather than in our comfortable environment doing homework problems. So, so talk about how to diagnose your learning algorithm. Right? So here we don't assume you have any implementation issue. We assume your implementation is correct because throughout this semester, you must have accumulated many good experience in debugging those models. And we assume that everyone is able to implement a correct learning model and algorithm. Then the problem is that how to diagnose the bottleneck of your learning model, right? And to overcome those bottlenecks, what kind of strategies can we use? And the second, if you look at in a bigger scenario, right? In practice, your machine learning model is always embedded in a much larger, a giant system, right? And in this giant system, their output will give you the error of your the whole system error will tells you how well this system works, right? But then the problem is that how do we know which error is caused by a machine learning model and which errors are caused by other components, right? We need to do some kind of ablation study, separate analysis, and then find a way to improve each component of your system. And finally, we'll talk about in your job, right? In practice, if you in your company, if you want to inject machine learning into your favorite task, what kind of strategy you should choose? So first, diagnosis, right? So suppose you have built up a SVM or logistic regression for spam detection problem, right? You want to detect spam emails, right? You obviously follow the best practices for finding hyperparameters like cross-validation, right? But your classifier has only 75% accuracy. Then the problem is that, can we find out the reason? Which factors or which problems limit the performance of your classifiers, or how can we improve them, right? So here again, we assume there are no bugs in the code. The code is right. So let us look at different ways to improve a model, right? Those are commonly used tricks, right? For example, we can try to add more training data, right? We can increase the data amount, right? Or we can modify the features, right? We can either use more features or use fewer features, or even use another set of features. And also we can try to tune the training process, right? We might need to run more iterations, especially for stochastic gradient descent, or we switch to a different learning algorithm, like we use gradient descent rather than stochastic gradient descent. Or we even can switch to another classifier, right? We use artificial neural network rather than SVM, or we kind of add more regularizations. So in a nutshell, there are a lot of like different tricks. But the problem is that those tricks are kind of tedious. There's so many, and if you just blindly try a few, there's no guarantee you're gonna work, right? And the success really depends on luck. Okay? So of course we don't want to do some blind combination of those tricks. We want some guidance. We want to diagnose some reasons, and driven by those diagnosis results, we can selectively or smartly to use one or combine a few such kind of tricks to improve our model. That's the idea. So regarding diagnosis, right, we need to first think of what kind of problems, right? What kind of problems may cause the issue of the model. Right? So here are several very commonly same problems which limit the performance of the model. Right? First, overfitting. So this is something we have discussed. I have emphasized again and again, right? You overfit your training data, right? The noises in your training data kind of twist or mislead the learning of your model, make the generalization performance bad, right? And the second problem might be underfitting. That means your data, your model is kind of like too simple. So this true function or true relationships are quite complicated, but you just fit them with a line, right? Of course, that won't work. So it's called underfitting. The third is regarding your learning behavior. Maybe your learning has yet converged, and then just stop it. Especially like when you conduct stochastic gradient descent, we know that it's very hard to diagnose convergence, right? So many people just look at the training epochs and look at the performance and say, okay, maybe it might be right time to stop. But the truth is that your learning might not converge to a good point, right? And finally, that might be your metric. You might choose the wrong metric. Then this wrong metric tells you the model is too bad or too or perfect or not indicative at all, right? So later we'll talk about what kind of measure you should consider for different cases. So let us first look at how to detect the first two problems, like overfitting and underfitting issue, right? So as we discussed previously, right, overfitting usually can be viewed as you got quite high training accuracy, but your test accuracy drops a lot. Right? It means, okay, the training accuracy is much higher than the test accuracy. That means the model explains the training set very well, but poor in the generalization. This is likely that your model is overcomplicated, it's over expressive, flexible, it can fit everything in your training set, including the noises. Right? Those noises kind of twist your model and make your model less well performed on the new data. Right? It's overfitting. And how about underfitting? can imagine underfitting means that your model is too simple. It's not strong enough to capture patterns both in training and test data. Right? So we can expect that if both accuracies are unacceptable low, then it's likely that your model is kind of underfitting, oversimplified, or oversimplistic. Right? That means the model is too simple and cannot represent the target function or concept well enough. So that's one straightforward way to look at it, right? So we can try to more accurately to detect such kind of problems, right? By looking at learning curves. So for example, you can increase the size of training set, or you can axis indicates the size of a training set, and then just look at error, both the training and test error. So for the training error, naturally, right, when the training set is very small, it is easier to perfect fit the training set, right? When you increase the size of training data, well, it becomes harder and harder to get a zero training error. And you can simultaneously examine your model on a separate large test set. Right? We call it generalization error or test error. And then we can look at the trend of the generalization error, especially the gap between the generalization error and the training error. So if the generalization error and test error exhibits a large gap, what does it reflect? Overfitting, right? So meaning that, okay, you're doing well on the training error, but then when you generalize, it's pretty bad. So you see that some kind of large gap. Of course, when you increase training data, you assuming like you got more and more training data, you have like infinite amount of training set. All that means you can see in all the cases, well, your gap will finally converge to say 0 or very close to 0. But throughout this procedure, you can see that the gap between the training and generalization error is always quite big. Then that means it's likely your model is overcomplicated. By contrast, if you see your training error and the generalization error, their gap are quickly shrinking and quickly converge to the same high error. What does it mean? Underfitting, right? Because those two models, the models are too simple, right? It can neither well fit the training data nor predict the examples for the test data, right? So you can see their gap is much smaller, but unfortunately, they're going to converge to a high level of error. Right? So by looking at those learning curves, it can help you, in a more refined way to look at the problem. Right? It might be overcomplicated, and then you need to reduce the complexity. Right? It might be too simple. You need to switch to a more expressive model. Right? Any questions so far? Okay, so now let us look at those tricks, right? And see which trick cause which can help which problem, right? So obviously, if you're using more training set, it can help with overfitting, right? So if you larger and larger training set, that means your model, although expressive, when it's trying to fit larger and larger data set, is kind of get closer and closer to the true function, right? You're going to reduce in the gap. And if you use more features, actually can help with underfitting, right? Because use more features, they actually expand the hypothesis space. You add more parameters in your model, right? You can imagine that your model can be more flexible, more expressive. If you use fewer features, essentially to reduce the model parameters, you can make your model space smaller. So it should help with overfitting. But if you use other set of features, well, the effect is kind of dependent, right? It might help with both overfitting and underfitting. It really depends what the new features are, right? What are the new features? And also in the training procedure, right? When you add regularization, right? When you enhance regularization strength or whatever, it could help overfitting, help with overfitting. Because when you regularize, when you put larger regularization strengths, that means they kind of give more penalty over those overcomplicated models, right? Any question? Everyone comfortable with this? Oh, you can use more features. You can even choose another classifier. Like if you use linear classifiers, you might feel it's underfitting. Then I might switch to artificial neural networks. I mean, those strategies listed here are not exhaustive. There are many other strategies, but here we want to emphasize that when you list all possible strategies, you need to be clear what can this strategy help. For example, use more features we expect it to help with underfitting. Right? Use fewer features, we expect to have overfitting. Right? So you need to know what's the benefit of using each strategy. Then you can decide which strategy should we choose. And another question? Okay, so now let us look at the problem of learning. Right? What if your learning behavior is not good? Like your learning even does not converge, right? How do we detect this problem? So the typical strategy will be like, okay, if the learning is framed as an optimization problem, just track the objective. I believe everyone has done this, right? You have done this a lot, right? So you just look at along with more and more updates or iterations or epochs, how does the objective function change? Right? And if you look at this point, obviously, this point shows the learning has yet converged, right? But for this part, if you see the learning curve is very flat, right, then you feel much more confident to say, okay, your learning converges here. That's why we always ask you to look at learning curve. Right? But what if the learning curve is like that, right? So of course we know at this point learning has yet converged, but how about here? Well, it's hard to see, right? It's really hard to see. Well, you can see, okay, the tangent or the slope here is quite small, but looks like there's still a tendency to go down, right? So this is kind of like more subjective. You can decide to stop here and then you test on the held out data set and see if it is good, or you can wait for more iterations to see if it can further go down. But in either way, watching the learning curve can give you a lot of intuition, right, and guidance. What if a learning curve is like that? Well, that means something must be wrong. You might have a too large learning rate in your stochastic training, right? Like some students have shown me like their learning curves like that. I said, okay, there must be something wrong. Your tuning, your parameter setting, whatever. Yeah, you need to have some trends like that. There might be some perturbation here, but it's fine. Right? But if you have such kind of like, wow, the perturbations and something like that, there must be something wrong. So learning curve is actually very informative. It can give you a lot of like guidance. So it's always good to track the learning curve. Right? It helps to debug. And if you use stochastic gradient descent, the objective function will slightly increase occasionally, right? But not too much. So if you're conducting stochastic gradient descent, typical behavior will be something like that, right? So at the beginning, you can still say, let me. Okay. It's typically like something like that, right? Right? You can see the perturbation in this learning curves, but the trend here is still clear. That's the normal behavior, right? If your learning curve is something like that, there must be something wrong. Okay, so now let us look at the strategies here. So those strategies are often used to find better training, right? So whenever you use a different algorithm, you track the objective for the convergence. Of course, you can run more iterations. You can use different classifier, right? But whenever you use these models to detect or to check if the training procedure is good, like track the objective for the convergence. Right? Okay. So now we can talk about how to diagnose these first three problems and what is the strategies to deal with these problems, right? Now let us look at the measurement issue. So this is something people might often ignore it, but it's very important because when you do the homework project, we ask you to calculate classification accuracy, we ask you to calculate the mean square error, well, you just follow our instruction, right? But in practice, your task is different. It might not be good to use this common use metric, right? And sometimes adopting those common use metric can lead to absurd conclusions. For example, if your data set is unbalanced, right? If you just calculate the prediction accuracy, that can be highly misleading. For example, you might have 1,000 positive examples, but only have one negative example. Even give a stupid classifier always tells the prediction is 1. Your classification accuracy still get 99.9% accuracy. Okay? So that doesn't make sense. And this is actually a very, very common scenario in practice. That means the labels are highly unbalanced. That's why in practice, the prediction accuracy are often not chosen as the golden standard. So how do we deal with unbalanced labels? Right here, we just do one metric. Another metric is called area on the curve, which you guys have already used in your calculus computation task. We give a very detailed literature explaining that idea. We'll refer you to that literature in our calculus computation website. But here we just introduce another measurement. It's called precision recall. So here we calculated just that precision, but there's another important metric called torque. So suppose this is your prediction of positive examples. This is a prediction P. You predict 8 examples to be positive, right? But among all the test examples, the true positive examples is 100. Okay? And among your 80 predictions, suppose only 20 of them are correct, meaning that you predict 80 positive examples. Among those 80 positive predictions, 20 are correct. So what is your prediction precision? Just 20 over 80, right? You predict 80 positive predictions, and among 80 positive predictions, only 20 of the predictions correct. The precision is 20 over 80. This is called precision. But there is also another measure called recall. It just asks you to check what is the fraction of the positive examples can you correctly predict it, right? So you got 100 positive examples in total, right? But you only give 20 of them as positive prediction. So the recall now becomes 20 over 100. Right? So you can see these are two different numbers. One actually measures how accurately your models make the prediction. The other actually measures how complete your model can recover all the positive labels. Right? So that's why we call the second metric as a recall. And in practice, we use the F measure. That is, we do the harmonic mean of precision recall together to give a more comprehensive evaluation of the model, rather than just look at the prediction accuracy. If it's just prediction accuracy, which is just precision, right? You can be very easily fooled, right? Okay. So now let us take a look at so here we discussed suppose your learning model are separated, right? And you're just trying to analyze what is the current bottlenecks, which things cause the bottleneck of current model, right? And you want to figure out the ways to improve the model, overcome these bottlenecks. But now let us look at what if your model now is deployed as a component of a joint system. And then given this system performance measure, we want to know which part of the error comes from your model, which part of error comes from other models, other components. It's not necessarily machine learning component. So in our class, we assume this is your work, right? You only deal with the ML code, you're doing a separate problems, you just test and investigate the behavior of your machine learning model. Right? But in practice, this is where your machine learning code is. It is always integrated with a lot of other components to form a joint system. This might be an online advertising system, it might be some recommender system in Amazon, it might be some ranking system in Google, etc. Right? So you gotta have a, oh, sorry, let me plug in the charger. The input of your machine learning model actually depends on many other components, like data collection, data verification, feature extraction steps, right? And then they feed them to the ML model. The ML model's predictions analysis will further feed to other components, right? So they're a complicated structure, right? Then many components are coordinating together, right? So in general, the machine learning plays a small role in a larger application. So because to conduct machine learning, you need some pre-processing step, you need some feature extraction step, and of course, this feature extraction might involve other machine learning based methods as well. They also do some data transformation, data cleaning, and all kinds of stuff, right? Then the natural question is that how much do each of these components contribute to the final error, right? And we need to conduct such kind of error analysis because we want to improve the overall performance of your system, right? So when we watch the system, it can only look at the output of the system and say, what's the performance, right? And once you got the performance, you need to go back to say which component takes the most responsibility so that we can focus on improving that component. So I want to explain the error analysis steps by using this example is a typical text processing pipeline. Right? So suppose you want to do some text mining applications, right? So your raw data will be a bunch of text, which may be crawled by your web spiders or any other collecting procedures, right? And then you need to first do extract the words and remove the suffix, right? To remove the transformations, then put them together. Like they might have a passive tense, might have a present tense, they might be passive voice and so on, right? You need to convert them to an identical form. And then you might need to do some parts of speech tagging, right? To see if this word is just a verb, just noun, or named entity. And next, with those part of speech tagging and also words, you might conduct some parsing, build some parsing trees. This is called semantic analysis, right? You look at the structures of those sentences, right? So you can extract the semantic meanings and then combine all those results. You're gonna feed them to some machine learning based applications. Like you want to predict what's the likelihood, who will win the president election, right? Or what's the trend of some opinion, public opinion, or for some topic, and etc. A lot of some kind of applications, right? So, and we can see that throughout this pipeline, we have several steps, right? And each of this could be machine learning driven, right? Those could be machine learning driven, those could be machine learning driven, those could be machine learning driven, or could be some other models driven. Could be done by manual work, like deterministic. But each component is also error prone, right? Not only the end machine learning model, right? Those components can give errors as well. And given the final performance, like your end performance, like 80% accuracy, right? We would like to know how much do each of these contribute to the error of the final application. Right? So once we know that, we know, okay, this might be the bottleneck, then we need to improve this. Or this might be bottleneck, we might improve this, right? And how do we analyze those errors? We can sequentially plug in the ground truth for the intermediate components and see how much accuracy of the final system changes, right? Of course, we need to prepare some like a test data set, and you need to know what is the ground truth of each component, right? If they're done by human beings, right? Like highly experienced human beings, right? So if you just use the original components, right? You might have your end-to-end predicted performance accuracy is just 55% accuracy. But now, let us try to replace the output of words processing step by the ground truth words. Well, you say, okay, it increased to 60%. Right? And next, we're gonna replace the parts of speech tagging by the ground truth. It increases 84% accuracy. And we continue and replace the parsing tree with the ground truth parsing trees, 89%. And now you place the final output as the ground truth. Of course, you get 100% accuracy. So now, who can tell me which component is the bottleneck? Any thought? Yeah, right. So if we take a look at improvement, right, we find that if we replace the results of parse speech with the ground truth, the accuracy increases from 60% to 84%, right? So it gives the largest improvement. So that implies that the quality of this parse speech of tagging component is the key to improve the overall system performance, right? Then we can try to use whatever diagnosis tricks and something we have discussed in the previous section to improve that component. And then test again and see if our overall performance can improve. Right? So this procedure can repeat and iterate to do some analysis, right? To keep improving the overall performance of the system. Another commonly used trick is called ablation study, right? So ablation study is often the same with the so-called feature engineering. So suppose we have a collection of features and our system does well, right? You have extract a bunch of features and use them to form your feature vector and feed to your machine learning system, right? And look, suppose these are working well, but we want to know which features are giving us this performance. It might be just a few features are critical, right? The remaining features just garbage or useless. Why should we store them, process them to occupy our computational resources? So then we usually do the ablation study. This is very common used in online advertising or recommendation systems. A lot of engineers are doing such kind of things. Right? So the common strategy will be evaluate a simpler system that progressively use fewer and fewer features to see which features give the highest boost. So it's kind of similar to the processing we have done this. Right? We might just look at those features group by group, and we just gradually prune one group of features and see if the performance drops or even improve. Right? You continue to do this and you see which group of features is inclusion or deletion can cause the largest performance change. Then they give you a clue of the importance of those set of features. And this is very important because right now people are not only satisfied by a black box neural network or something like that. We want our machine learning model to work, but we also want to know why it works, right? Which component leads to the performance, best performance, so that we can better control the model, we can better recognize the model, and also probably also the data itself. Okay, those are about the common suggestion for the error analysis. Again, this is not an exhaustive strategies. We just give you a common used practice and devices. In the future, if you're trying to apply machine learning in a variety of applications, well, you have a lot of choices, right? So you can base upon that and develop our own strategies. And finally, we want to talk about in a work, right, like in a company, right? If you want to use some machine learning to finish some task, how should we develop a machine learning models and deploy them in practice, right? Suppose our task is to classify a fish. Right? So you want to build a classifier that identifies whether a real physical fish is salmon or tuna, right? How do you go about this? There are kind of like two strategies. One is called slow approach. You're going to carefully identify features. You get the best data. You carefully design the software architecture, and then maybe you design new algorithm. Then you implement it and hope it works. Right? So we call this approach is called research style approach. Right? It gives you perhaps a better or even new approach. Right? It is good to use them to conduct research. But I can tell you, in practice, if you do this in your company, it's very likely you got fired or be warned by a boss because they cannot wait for 3 months to let you just collect a bunch of features. They want to see the results as quick as possible. So in practice, we're gonna always use the hackers approach. Don't try to build up perfect models and algorithms at the beginning. Try to get something work. Try to get something useful. It's not perfect, but it's working. It is useful. And then try to use all the strategies we have discussed to make it better and better. This iterative procedure is the most favorable procedure in practice. So you first implement something, you might use some stupid classifiers like linear classifiers or some decision trees, right? You have source code, just deploy and say what's the performance. And then you find the performance is not very good, but at least it is working. And then you try to improve that. You try to analyze the bottleneck. It might be the data bottleneck, might be the training bottleneck, etc. Right? And use all those strategies to iteratively improve them. Right? That's the always rule of thumb in practice. So the advantage is that it can give you faster release of algorithm, and it will have a solution for a problem quicker. And of course, when you deploy those machine learning models in practice, you always need to watch for the right evaluation metric, right? Because practical application is much more complicated. So you have to sometimes you have to define your own evaluation metric to ensure your model works, right? So that is very important, and also be aware of contamination. Right? Ensure that your training data is not contaminated with test set. Right? So this is a very basic principle, but it's often, I mean, even like experienced machine learning engineers can make such kind of mistakes. So if you overlap your training set and test set, then your test accuracy is not meaningful at all. So whenever you got very good performance, right? Don't be too excited, right? Don't open champagne. Try to be suspicious of the perfect predictions. So what else should we take care of, right? be aware of the bias and bias trade-off, meaning that overfitting, underfitting, try to find out the best trade-off between the model complexity, right? And overcomplicated models and oversimplified models, right? And be aware the intuitions may not work in high dimensions. Right? So we have good intuition in two-dimensional space, one-dimensional space, or even three-dimensional space. But for high-dimensional space, there's no proof or no picture. So don't try to simplify. Don't try to consider a high-dimensional case will be the same as two-dimensional case. And also, don't be misled by the theoretical guarantees. So you see that there are a lot of theory, right, which are important, but you see that many theories, they have some pre-assumptions. So if you ignore the pre-assumptions, then your conclusion based upon the theories are totally wrong. So, but unfortunately, due to the complexity of the practical applications, those theoretical assumptions are often not true. And big data is not enough. More data is always better, but given the more data, we often need to clean the data. That's why the data cleaning procedure is also a very important pipeline step, right? And also, learning requires knowledge to guide the learning, right? To guide the learner, right? Machine learning is not a magic wand. You just feed them and you get good results. You have to combine all your knowledge in tuning, in data collection, in the domain to improve the model. So those models include, those knowledge includes like which model is the right one for this task, right? Which learning algorithm really work better for this particular case, right? And also we should do the feature engineering, and implicitly, these are all the claims about nature of the problem, right? And miscellaneous advice, like first, we always use a hacker's trick, right? Learn simpler models first, try to use simple models to fit data and see if it works, right? If it works well, your job is done, right? If it doesn't work well, you get an extra baseline from which you can compare with. And another common use trick is that ensemble seems to work better. You can first develop a single models, and if you want to further improve, and there seems not much improved space, you try to use ensemble approach. And finally, you might stop for a while, right? Don't be too fascinated by machine learning. Right? Think about whether a problem is really learnable, right? Is really suitable for machine learning. Okay, those are all our advices, and we appreciate your hard work throughout this method, and wish all of you have a great success in the future. Thanks.